All right, let's dive in. Today, we're going to crack open the engine room of artificial intelligence and really look at how these incredible systems, well, how they learn. It's a process that's absolutely fundamental, but as you're about to see, it's also in the middle of a pretty radical transformation. So let's get into it.
You know, it's the question behind pretty much everything these days, from your phone's smart assistant to these huge scientific discoveries. How do these massive neural networks get so incredibly smart? Well, the short answer is a process called backpropagation. It's the absolute cornerstone of modern machine learning. But the way it's been done forever is starting to show its age.
I want you to think of the classic way of training an AI like a single enormous factory. You know, everything's happening under one roof on a super rigid assembly line. All the parts have to be in the exact right place at the exact right time, all working in perfect sync. And look, for a long time, this model worked wonders. But the world of AI, it's changing, and it's changing fast. Yeah, that whole monolithic factory idea, it's becoming a massive bottleneck. See, AI is moving out of those giant data centers and into the world. It's on our phones, it's in our cars, it's spread across huge networks of devices. And that old, centralized assembly line, it just can't keep up. It wasn't built for this new, flexible, distributed world.
This slide really just lays it all out, right? The old way, that factory, it's centralized, it's synchronous, it just assumes everything is in one place. But what we need now is a distributed network, a team of collaborators or agents that can work together no matter where they are, in the cloud, on your phone, using all different kinds of computer hardware. The rigid assembly line has to go. It's time for flexible collaboration.
So here's the bottom line. Traditional backpropagation is, well, it's brittle. It's built on this assumption of one giant unified system. It totally struggles when you try to mix and match different processors, like your standard GPUs and those cool new neuromorphic chips. And it is incredibly inefficient for the kinds of small, powerful AIs we want running on our phones or out on remote sensors. It just wasn't designed for that job. Okay, but what if you could teach all those different parts of the AI to talk to each other? What if, instead of that rigid assembly line, we just gave them a shared language for learning? This is where things get really interesting. Our source material introduces a fascinating solution called the Crisp Backpropagation Protocol, or CBP for short. At its very core, CBP completely reframes the whole idea of AI training. It says, hey, let's stop treating learning as one single internal calculation happening inside one giant machine. Instead, it turns learning into a communication protocol. It's a set of rules for how different independent AI agents can swap information and learn together, no matter where they happen to be.
This quote from the source material absolutely nails it. It's not a top-down monologue from some central computer anymore. It's a dialogue. It's a conversation between the different parts of the network. Every agent can chip in, give feedback, and update itself. It's just a much more dynamic and resilient way to do things.
So if the old way was that one giant factory, the new way is more like a network of specialized artisan workshops, right? Each little workshop is an expert at its own specific task. And CBP? Well, CBP is the universal language and the super efficient shipping system that lets all of them collaborate on a really complex project, sharing blueprints, materials, and quality reports just seamlessly.
So how does this shipping system actually work? The secret sauce is something called a cognitive packet. And honestly, the best way to think of it is as the magic shipping crate that carries all the vital information between all of our little artisan workshops.
And this whole system relies on four main types of these packets, these crates. You've got your forward packets. They carry the initial data, kind of like the raw materials. Then you have loss packets, which carry feedback on how well the network did. Think of it as a quality report. Then you have gradient packets, which carry specific instructions on how to improve, like a corrected blueprint. And finally, optimizer packets, which are used to negotiate the actual update rules, kind of like all the workshops agreeing on which tools they're going to use for the fix. The whole process is this really elegant five-step flow. First, the raw materials travel forward through the network. Second, a quality report gets generated. Third, the correction blueprints get sent backward. Fourth, the workshops all agree on the tools and the process. And finally, each workshop updates its own machinery and the entire network gets just a little bit smarter.
Okay, so what does this new model really unlock? What are the actual advantages of this artisan network over that old clunky factory? Well, it turns out this thing has some serious superpowers. Because learning is now all about communication. You can do some amazing new things. You can radically compress the data that's being sent between agents.
You can distribute the learning process across a whole swarm of devices. It even allows totally different types of hardware to finally play nice and work together, all while making smart trade-offs between speed and energy use. And listen, we're not talking about small improvements here. Just take that data compression. By only sending the changes in information, that's a technique called delta encoding, CBP can slash the amount of data being transmitted by up to 90%. That is a total game changer for learning on devices with limited bandwidth, like your phone.
When you put it all together, the result is just crystal clear. Compared to the old, centralized ways, this new protocol delivers huge gains. It's got better scalability, so the network can grow much bigger. It's got better resiliency, because hey, if one workshop goes down, the others can adapt. And it has way better overall efficiency, using less energy and data to get the same or even better results.
So what does this all mean for the future? Where is this new language of learning actually going to take us? This, my friends, is where things get really, really exciting. The potential applications are just vast. I mean, we're talking about swarms of robots that can learn and coordinate on the fly. We're talking about smarter edge devices that can learn right from their own environment without constantly sending your data to the cloud. And we're even talking about more advanced stuff like federated learning, neuromorphic computing, and even hybrid systems that mix classical and quantum computers.
This right here is the key that could unlock true swarm intelligence. Just imagine it, a fleet of drones mapping a disaster area, or a whole network of environmental sensors monitoring a forest fire. With CBP, they don't just collect data, they can learn from it and from each other in real time. They can adapt their collective strategy as one single intelligent system.
And honestly, that is the most important thing to take away from all this. The CRISP backpropagation protocol isn't just a simple upgrade for that old factory. It is a fundamental shift in how we think about this stuff. It's not about building one giant, all-knowing brain anymore. It's about creating an entire ecosystem where countless smaller, specialized minds can collaborate, communicate, and become intelligent together.
And that leaves us with a final, pretty fascinating question. As we move from these monolithic factories to these collaborative swarms, we're not just changing how AIs learn, we are changing what they're capable of. If a whole network of AIs can learn and adapt together, what truly complex, global challenges could they help us solve? Thanks for tuning in.